It's a pleasure to be here. I am based in Eindhoven, but as you've mentioned, I'm also trying to work in Ghent and Vrije University of Brussels. And my main research topics where I work is spectral graph theory. I will give you an introduction to the topic and the main tools we use. But sometimes here and there, I like to try other things like optimization or a bit of quantum. You will see what I mean by that. So this is the outline for today, the content of my talk. I will split first. I will start discussing a bit the background we need to state the main results and to understand a bit the story. Later on, I will go to explain some spectral bounds. Spectral bounds are just eigenvalue bounds. We will see how we can optimize such bounds using MLPs, basically. Later, I will give you a glimpse of my only approach to quantum stuff. So sorry about that. This talk is mostly spectral graph theory. There is a bit of quantum at the end, but yeah, okay, we will see that. And then finally, I will end up with some open problems and closing remarks. So let's get started with some background. Here, this is my basic slide. I always use it because not only because it has the Petersen graph on it, but because it represents the beautiful Sagrada Familia from my hometown. And also to indicate that I'm going to be working with adjacent symmetrics of a graph. So is this a real symmetric matrix of 0, 1s? Therefore, it guarantees that it has a real eigenvalues, a real spectrum. And what I also want to note here is that I'm going to be denoting the spectrum in two ways, the eigenvalues of the graph in two ways, sometimes considering all of them repeated with lambdas. So in this case, for the Petersen graph, is this a spectrum? But sometimes I'm going to be using, for convenience, this notation where we just take distinct eigenvalues. So then we denote the eigenvalue, and then as a superindex, the multiplicity of the corresponding eigenvalue. So here you can see the example for the Petersen graph again, okay? So when I talk about thetas, it's distinct eigenvalues. When I talk about lambdas, it's repeated eigenvalues, okay? Okay, another definition I will need later on, not at the beginning of the talk, but mostly towards the end results, is that one of a K partially walk regular graph. A K partially walk regular graph is a generalization of what is known as walk regular graph. Walk regular graphs were introduced by Gottschall and McKay. I'm not remembering which year actually. But the definition of this concept is just that the number of closed walks of a length at most K is the same for any vertex, okay? So it only depends on that length, the number of closed walks of certain length. Then every simple graph is K partially walk regular for 0 and 1, and every regular graph is in particular 2 partially walk regular, okay? Because the degree in the main diagonal is just the same. And it's also known, there are several characterizations out there in the literature, but maybe this is just nice to know that if a graph is K partially walk regular for every K, this happens if and only if the graph is actually walk regular. And here I compute an example of a graph which is walk regular, for example, that because, okay, it's known that walk regular graphs contain vertex transitive and distance regular graphs, but it's not always true that a distance regular graph is walk regular. So here I give you the smallest example of such a situation. This graph is walk regular, but it's not distance regular. It has 12 vertices. Okay. Then I need.
Aida,
yes.
Maybe could you just remind me what closed walk is?
Yeah, a closed walk is just a walk of certain length from a vertex to itself.
Thanks.
Yeah, no problem. Okay, then we also need the definition of graph powers. This is a bit more natural definition, and probably you have seen it before. But just in case, I'm going to remind it to you. So given a graph, the graph power of it, the kth graph power, is formed or is obtained by adding all the edges between the vertices which are at distance at most k. So imagine we start with j being this long cycle. If I want to calculate the 2 power of j, I just add the extra edges that are making the distance at most 2 possible. And then g3 is the same, adding the edges that are the edges between vertices which are at distance at most 3, etc. Always move on, okay? So the graph gets denser and denser. Okay, and in a second you will see why I need this graph power definition. Now let me move on to the main character of this talk, the independence number. So everybody knows what the dependence number is, but maybe not everybody knows what the k-independence number of a graph is. This is a very natural definition and extension of independence number. It's just the maximum size of a set of vertices which are at pairwise distance greater than k, okay? So in particular for alpha 0, for k0, we obtain the number of vertices, and for k1, you obtain the classical independence number of a graph. So just as an example, like this is the two independence number of this cycle graph. Okay. And this is an important remark. The k-independence number is just the independence number of the graph power. This, we're going to be using it through the talk. Okay. So in particular, in the previous example I gave you for alpha 2, you can see that it's the same as alpha of the 2 graph power. Okay. And in particular, it's 2, this value. Okay, let me give you a bit of context of what has been done for the k-independence number of a graph. So in 93, Kong and Zhao proved that actually the complexity of determining the complexity of the k-independent set problem is NP-complete for general graphs. So it's a hard problem as expected. And they also prove in particular that the problem remains NP-complete if one focuses on regular bipartite graphs for certain cases. This is here important maybe to note that the bounds that we are going to be using and providing only depend on the spectrum of a graph. And it's important to remember that the spectrum of a graph can be computed, or is known that can be computed in polynomial time. And one more algorithmic result is that there are some heuristic-based algorithm also for the two independence number. And now let me go back to more to the results known for the k-independence number from the graph theoretic point of view and from the spectrum point of view. Firby and Haviland in 97 provide some upper bounds for the independence number for a connected graph. What they use here is basically the average distance to bound this upper bound, the k-independent number. Then in 97 also Fiol provide the first eigenvalue bounds for the k-independent number using alternating polynomials. I'm not going to define what they are, but they come as a solution of a linear program. That's important to have. So the way to use Fiol's bound is to solve an LP, an optimization problem. And then other results, for example, also in 2005, there was these upper bounds for random regular graphs provided by Bayes, Duckworth, and Zitton. More results recently in 2019, Oishi and Taukia provide also sharp upper bounds for the k-independence number of regular graphs for certain cases. There were also sharp upper bounds for the two independence number of a tree. And recently, the k-independence number has been related to certain function of a connected graph. Okay. Now, let me give you a bit of overview of how the independence number relates to other things, other fields, basically. In coding theory, it's known that codes are k-independent sets in Hamming graphs. And in this regard, there were also the spectral bounds that were provided by Fiol. I will discuss this a bit more later, but can be used to prove non-existence of certain perfect codes in odd graphs, codes that attain the Hamming bound. Okay? More relationships with other combinatorial parameters, the k-independence number.
Codes. So does k denote the distance then?
Sorry?
So in the previous slide,
yeah,
this k would be the distance between code words, yes?
Right, yeah.
Or maybe twice the distance. Okay.
Yeah, I think it's k, the distance.
Yeah, thanks.
Yeah. And then the k-independence number is also related to the average distance, basically by bounds, not direct relation, but by bounding each other. And it's also related to the h diameter of a graph, which is the maximum distance such that there exists a set of vertices of cardinality h, such that any vertex inside that set of h vertices has distance at least that h diameter. Okay? So it's like a generalization of the diameter of a graph, and this concept was introduced in 99 by Chang, Delorme, and Solé. Okay. Now, related to the k-independence number, there is also the known k-distance chromatic number. So let me first define what it is, and probably you can already guess what this is going to be. It's just the chromatic number of the power graph, right? This is the easiest way to remember the definition. So it's also natural to see that upper bounds on the k-independent number directly give lower bounds for the k-distance chromatic number and vice versa. And we are going to be talking indistinguishably about bounds for alpha k or for gk, okay? Regarding to open problems for this distance chromatic number, there is a class of coloring problems that I would like to point out to you. There was a question by Mohar and Alon in 2002 that basically asked the following. They say, what is the largest possible value, the chromatic number of the power graph, so of the k-distance chromatic number, among all graphs with maximum degree at most certain number and girth at least certain number. Remember, the girth is the shortest cycle in your graph, okay? The case of K1 was a long-standing problem by Bising and was settled down asymptotically by Johansson in 1996 using some probabilistic tools, so don't ask me about this, but it's known to be resolved. For K2, this case was also solved by Alon and Mohar asymptotically as well. And for general K, the maximum that is known, as long as I realized, was there exist bounds. There exist sharp bounds that, basically give you an intuition of how this guy is lower bounded, this parameter, okay? And we are going to be using some of these bounds, especially the ones by Ross-Kang and co-authors. So the goal for this talk and the goal of this work basically was to extend two classical eigenvalue bounds for the independence number of a graph. Let me state which two bounds are we going to be extending in this talk. The first bound is due to Svetkovic. It's called the inertia bound because, as you will see in a second, it just contains the number of positive eigenvalues and the number of negative eigenvalues of the adjacency matrix of a graph. So this bound holds for any graph, so it's important. There is no condition required here. And it's a bit of a mysterious bound because the community doesn't know well when this bound behaves good. So this is a bit the story. This is the inertia bound. It's the first bound we will be trying to extend, studying further. And the second bound we're interested is called the Hoffman ratio bound. Probably you have used it or seen it before. Is a bound that holds for regular graphs only. And it only depends on the largest and the smallest eigenvalue of the adjacency matrix of a graph. And this bound, we know when it attains equality, right? So, well, here I put when is the case, but this bound is known when it's tight. This bound was proved first by Delsarte as ratio bound only for strongly regular graphs, and later on was generalized by Hoffman, and it was extended actually to regular graphs, which is how we know it now. Okay. Why are these bounds relevant? I mean, among other things, maybe the most relevant thing is that these bounds provide proofs of the Erdős-Corrado theorem, which is an important result in extremal combinatorics. Just applying them to the Neisser graph, so you need to know the spectrum of the Neisser graph. And then more things about why do we want to give spectral bounds for this k-independence number. We saw that the k-independence number is the independence number of the graph power. However, in general, even the most simple parameters that you can imagine of the graph power, they cannot deduce so easily, or they cannot deduce at all from the parameters of the original graph G, right? So one cannot just apply the previous bounds. That doesn't work like that. Because in particular, the spectrum doesn't follow, okay? So the spectrum of G and G kth are not related, or we don't know how this could be the case. So it's not known if the eigenvalues relate. It's not the case in this situation. So this is important. We're going to be providing bounds that only depends on the spectrum of the original graph, not on the spectrum of the power graph. Okay? That's why we care about new bounds for alpha k and not just reusing the old bounds. The main tool that you need to know, or the main result, basic result of algebraic combinatorics is this one that I state here, is that given adjacency matrix of a graph, the power of the adjacency matrix just counts the number of walks of fixed length k, because we are looking at the kth power, from vertex I to vertex j. Yeah, so you see this is actually the main link between algebra and combinatorics. We are counting things looking at powers of adjacency matrices. And the second main tool we are going to be using in these results is called interlacing. Interlacing of two sequences of real numbers. So one needs to be larger than the other one. That's the only condition. N and M are the lengths. Interlacing is a set of these two M inequalities that gives some relationship between these numbers in the sequences, okay? So in particular, if we want to visualize this in a more illustrative way, if we have that lambdas are the eigenvalues, for example, of the adjacency matrix, that's normally how we would use it, and mu's are some other eigenvalues of some submatrix or some other smaller matrix, then the interlacing, the name of interlacing comes from the case where the smaller sequence is just exactly one element smaller. Then you have really interlacing, as the name suggests, as the blue dots here say. But you can also have more sparse interlacing if M is smaller than N minus 1, as the red thing suggests here. But in particular, we care about eigenvalues. So I'm going to be applying interlacing for eigenvalues. So I'm going to be denoting lambdas for the eigenvalues of the adjacency matrix. so size n, right? And then mu's are going to be denoting the eigenvalues of a certain smaller matrix. You will see in a second which is this other matrix B. There are two cases for the matrix B, the smaller matrix. The one of the most famous cases is when B, the smaller matrix, is just a principal submatrix of the adjacency matrix. In this case, there is a very famous result by Cauchy that says that the eigenvalues of this principal submatrix B interlace, so it holds these inequalities with the eigenvalues of the big matrix, the adjacency matrix A. Okay, so this is the most famous interlacing result that probably you have seen. The less famous interlacing type is called when B, the small matrix, is the quotient matrix of the adjacency matrix. This happens when you partition the vertices of your graph into M sets, say. Then we can construct from this partition what we call the quotient matrix. The quotient matrix is an M times M matrix, which contains the average row sum in each entry of the block you're looking at in the partition of the adjacency matrix, okay? And then Hammers in his thesis proved that actually the eigenvalues of the quotient matrix of a symmetric real matrix partition interlace the eigenvalues of the regional matrix. So it's the same type of result, but now instead of B being the principal submatrix, B is considered to be the quotient matrix. These two things are very important because they provide the proofs actually of the main spectral bounds I just stated before.
Sorry, I missed this. How does this interlacing work if one matrix is much smaller? So like in which gaps exactly do these other eigenvalues fit? Yeah,
so the inequalities are here. Yeah, so you have lambda I always larger or equal than mu sub I. So you will have probably the eigenvalues in the sides. And mu sub I is the eigenvalues of the small matrix, larger or equal than the right eigenvalues of the big matrix. So yeah, if it's much smaller, you will have something like here, like much sparser, of course, and in between, though, distributed. Okay. But it depends on the graph, eh? There is no only, I cannot tell you exactly if it will be to the right totally or to the left totally, you know, like, yeah, it depends on the spectrum of the small matrix also.
Is lambda 1 always normalized? Is it 1?
No, lambda 1 is just the largest eigenvalue of the adjacency matrix, so it's not normalized necessarily.
Okay.
Yeah. Yeah, it's just a sequence of real numbers. Yeah. Any other question regarding this? Okay, if not, we move on. So this we saw. Okay, so now I state the two main types of interlacing, which is what we're going to be using in the proofs. Now let me give you a bit of an idea. Because I mentioned in general, the spectrums of the power graph and the original graph are not related, but in some cases they are. So let me explain what can we do when they are related. So I'm going to, first of all, we need to know when the spectrum of the power graph and the spectrum of the original graph are related. And this happens when the adjacency matrix of the power graph belongs to the algebra generated by the adjacency matrix of A. Or equivalently, if there exists a polynomial such that the polynomial applied on the adjacency matrix gives you the adjacency matrix of the power graph. Okay? This is the condition. And then, for instance, I'm not going to describe to you, I'm not going to define what these graphs are, but for instance, this was characterized that this happens when the graph is partially distance polynomial. It's a concept that was introduced by Fiol, Van Dam, etc. in 2011. So when this happens, when the spectrums are related, that means when this polynomial exists, that holds this condition, then we are going to see what can we say about this question by Alon and Mohar. Can we provide some nice bound for this question? And the answer is yes. And the main result we need to use for our bound actually is this other result by Fiol in 2012, that he proved that for regular graphs, he gave a bound for regular graphs. This bound involves certain orthogonal polynomials called predistance polynomials. I'm not describing them here, but it's just a sequence of orthogonal polynomials with respect to some scalar product, quite natural scalar product that uses the trace of the matrices. So this nice sequence of orthogonal polynomials provide a nice bound actually for what he calls this sum of predistance polynomials. Q to the k is the sum of orthogonal polynomials. And he gave an upper bound for this. And he characterized that this happens with, this holds with equality if and only if the spectrums are related. So recall that when there exists such a polynomial Q, that apply it in the adjacency matrix gives you something that is the adjacency matrix of the power graph. This is important to keep in mind, this condition in red. Okay. So forget about this result by now, it's not super important, but I just want to tell you that we're using this to actually prove our bound that answers that question.
Do the orthogonal polynomials depend on the graph here?
Yeah,
Okay.
yeah, totally. Okay, so using the fact that we know that this sum of predistance polynomials on the largest eigenvalue is always larger or equal than the sum of predistance polynomials in any other eigenvalue, D is the number of distinct eigenvalues. And remember that theta is the spectrum when we just consider distinct eigenvalues. And using the previous inertia and ratio bounds that I stated, we can actually give a lower bound for G sub k, for the k distance chromatic number, or for equivalently the chromatic number of the power graph. So, of course, we need the condition that the spectrums are related for making this bound to be correct, because we are basically using Fiot's previous result to prove this bound. Okay. But I don't know if you noticed, but here you already can resemble a bit an inertial bound type and a Hofmann bound or ratio bound type. Okay. And then, okay, how does this bounds actually help to answer or to try to get insights on the Allen and Mohar's question? That's maybe the next question that pop up in your mind. Maybe the first thing is like when we try to study when these bounds are tight, for which graphs these bounds are tight, it's good that Ross Kank sent me an email when we published the first paper saying, okay, I think we are working on different directions, but we are kind of looking at the same type of parameters. Like they were working on the k distance chromatic number from the extremal point of view mostly, and we were working from the algebraic point of view. But it's good he mentioned that, because then I started reading his papers, and we realized that one of the lower bounds, they provide bounds. Some of the upper bounds come from the probabilistic method, but the lower bound comes from some direct construction using some incidence structures, in particular some bipartite graph with some conditions. So in that paper, they introduced a new product called the balanced bipartite product, which I'm not going to bother you with the details of the product. They introduced it in this paper I mentioned here. The only condition they require is to have two bipartite graphs with the same size, the same order of the stable sets. And then you obtain a new, he calls it balanced bipartite graph. So this was nice because we realized that his so the structures that gave sharp bounds for him were also sharp in some cases were sharp for us as well. So that was nice. So for the Hofmann type bound, for the second bound that I state here, this one, that product, that construction that Kang and Pirot introduced gave us also sharp bound. But okay, you might wonder, but are there more cases when the spectrum of the original graph and the spectrum of the power graph are related? And the question is yes. And this is important here because this is when we go back to the Allen and Mohar question. Another case when the spectrums are related, what I put here in red, so when this condition holds, is when the graph is regular with fixed girth G and K satisfying some condition in terms of the girth. Okay? Because using our paper from 2016 with Van Dam and Fiot, we proved that in this situation, the graph needs to be K partially distant regular with certain intersection numbers. And don't worry if you don't know this definition of K partially distant regular, it's just distant regularity up to distance K. It's the same as distant regularity, but you don't require for every K, but up to distance K only. And then the reason I'm using this result here, or that I stated here, is just because in this situation, we can calculate explicitly how this polynomial looks, because otherwise you might wonder, okay, this is a very general condition. How do I know how to calculate Q to QK, this sum of predistance polynomials? So in case that the graph is regular with certain girth and K, I know exactly how these polynomials look like. And then we could implement our bound and test it for some real graphs in Sage. Okay? So that's a bit what we did. So what we did is like we test how our bound behaves for some named Sage graphs. And these are some of the graphs for which our bound, with, of course, the girth is fixed and the K depends on the girth, as was stated in the previous slide. These are the real values, but are also the values of our ratio type bound. Okay? So the reason this is important is because it gives you a case when the spectrums are related and also when we know how to calculate such a relation between the spectrums, such a polynomial Q. Okay?
What is the flower snark?
Sorry?
What is a flower snark?
Don't ask me because I don't remember. We just went through all the namespace graphs that are on the database and tested, but I don't remember.
Okay.
Sorry. Yeah, there were many graphs. To be honest, I saw many graphs that I had no idea they exist, and even less than they have a name. So that was a bit new for us also. Yeah. But of course, in general, the spectrum of the power graph and the original graph are not related. So this is the case we're interested because this is the most general case. So the remaining of the talk, I'm going to be addressing this case. Okay. So the line of work, I'm going to announce it here because otherwise it might get a bit confusing. These are the three main papers we have on this topic. And on the first paper, we just extend naively the bounds, the inertia bound and the ratio bound for the powers of the eigenvalues. In the second paper, we realized, okay, maybe for some graph families, we can find the best polynomial, the best combination of powers of eigenvalues that gives us the best bound. And finally, in the very recent work, what we did is just, okay, let's provide methods that compute the best polynomial for any graph in general. Okay, so it really depends what you're interested. Of course, for the first type of result, we were able to prove tightness. But if you care about in general, that's harder because it really depends on the graph. So it's different contributions in this regard. So first, I'm going to be speaking a little bit about the first spectral bounds, not too much, because this has been improved later on in the paper, so just a little bit. This was joint work with Chao and Tate from US. So to make an extension of the inertia bounds, the first extension we did at least, we had to introduce new parameters, and these parameters are going to be through the rest of the talk. So let's try to remember these definitions I put in red. W in small letters, it's going to be, if you look at the power of the adjacency matrix, it counts closed walks, right? We saw. If you look at the main diagonal of that power of the adjacency matrix, there you get all the closed walks from a vertex to itself of a certain length, right? K in this case. So W is just the minimum number in the main diagonal of the power of the adjacency matrix. Okay, that's what it means. And capital W is just the maximum number of those values on the main diagonal of the power of the adjacency matrix. That's all what it means. And this is what's going to be popping up all the time in the results. So the extension of the inertia bound, actually, instead of just having the number of positive eigenvalues and the number of negative eigenvalues, as is Svedkovic proof, we require to have that the powers of the number of eigenvalues whose power is larger or equal than this number, or the number of eigenvalues whose power is smaller or equal than the maximum value in the main diagonal. Okay, that's a bit the idea. But it resembles the inertia bound, as you can notice. Instead of zeros, now you have these values here. Okay. And of course, as a result, you obtain this Svedkovic bound, the inertia bound. We were also able to prove a construction that gives equality. Well, I'm going to just announce it here. The proof is non-trivial, so I'm not going to put too much detail on the explanation, but at least that you see that you can start with a complete graph, remove an edge, and then make copies of this complete minus an edge, m copies. Index vertices where you remove the edge, and then add a path with an external extra vertex of length k, exactly. And we call this graph G. So this is the graph that attains equality for one of the families that attains equality for our first bound. This was hard to find, actually, because as I mentioned, for the inertia bounds, even for the simple case of alpha, it's not really well known which infinite families of graphs hold it with equality. So for us, it was quite some work also to find this guy. And the second bound we extend was the ratio bound, or the Hofmann bounds. So the first extension we did, I'm not going to prove this once here because we did a different version later and I like maybe more the other proof, but the first extension uses the expander mixing lemma extended. So that's why we need as a parameter here to define some things that maybe sound to you a bit like expander graphs. We're going to be using ND lambda graphs, which is a notion that appears in some Alon papers, I think, which are regular graphs with of course, the largest eigenvalue is always a degree, and then you have that lambda, maybe that's an important thing, it's just the maximum in absolute value of the second largest eigenvalue and the smallest eigenvalue. And now instead of looking at W capital being the maximum number in the main diagonal of certain length walks, now we look at walks of length at most k over all the vertices. So it's slightly different, but same style. And for K1, this bound actually just gives you the ratio bound, no? The well-known ratio bound. Okay, and this type of bound, Hofmann bound, performs well for graphs with good spectral graph, so basically expander graphs, because these graphs have are sparse and they have a strong connectivity properties. And this is kind of natural because in the proof, what we use is just an extension of the expander mixing lemma. And as a corollary of this bound, of course, you obtain Hofmann. Okay, but now we are in a situation where we have some extensions of these spectral bounds. And the next question is like, what about more general scenario? Now we are just looking at a to the power of k, right? I'm working with the powers of the eigenvalues, but which is the same as working up with the powers of the adjacent metrics. But why I don't look at linear combinations of these guys? Maybe I can get a better bound even for alpha k.
Aida, can I interrupt you once more?
Sure.
In the previous slide, you mentioned expander graphs, in particular that they're sparse. Can you remind me why sparsity is important?
Yeah, because so the guys who have this guy very large, the lambda, are normally really good, really sparse graphs, but they're still very strongly connected.
Yeah, but I know why is sparsity important for you? I don't remember. Is it something you use in the proof or?
We don't use in the proof sparsity actually, but the fact that we use expander mixing lemma, which behaves good for sparse graphs with strong connectivity problems, I think that is when it pops up. We don't use it explicitly, if that's maybe a question, in the spectrum or anything like that. We don't really use it, but.
Yeah, I don't recall the sparsity being important in the mixing lemma. But,
I might be confused maybe. Well, now you're making me doubt. I'm not totally sure then. I mean, I remember we don't use it explicitly in the proof, but
okay.
Yeah, maybe sparse is not the right word. I need to check. Yeah, thank you. Okay, so we were here like this. Okay, next natural question is like, okay, can we improve these bounds actually? Can we look at them for any polynomial? Probably the answer is yes. Because for what you can do is like take a polynomial, and this polynomial has as a principal submetrics. You can always reorder the vertices. Take the principal submetrics, the guys that correspond to an k-independent set. And we know that the polynomial, any polynomial of degree k, apply it in the adjacent symmetrics, can have as a principal symmetrics this U, which is a k-independent set. And this is just, this P of A is just a combination of powers of the adjacent symmetrics, so a combination of closed walks of certain length, right? So until now, as I mentioned, we just care about, or we just use k powers of the adjacent symmetrics. But can we do this? Can we do better? And the answer is naturally yes. Of course, you lose then a bit of control, because then the bounds will be much more general, and then you don't know, you cannot prove theoretically maybe when these bounds are best, when they are tight, etc. So in the first project, we were with Coutinho and Fiol, and we managed to indeed push these bounds a bit farther and farther than the previous ones, in the sense that now I'm not working with lambda to the power of k, but I'm just working with a general polynomial. I still don't require any regularity or anything, so that's good. And then in particular, we obtain the previous result. And as you see here, we still have in the proof these W's, which are these parameters, which are just the maximum entry or the minimum entry of the power of the P applied to A, so the linear combination of powers of the adjacent symmetrics. Okay. So these bounds will be interesting if one can actually provide a method to compute such a polynomial. Otherwise, this bound is just purely theoretic, not really practical interest, right? So this is what we will later do. Let me give you the proof of this bound, because it's kind of nice, simple illustration of interlacing, of Cauchy interlacing, the first type. So assume your k-independent set, we denoted U. There X is a k-independent set of size U in G. So you have P of A, which is your polynomial applied to the adjacent symmetric, so it's just a linear combination of powers of A. Then you can reorder the vertices such that the k-independent set belongs to the first vertices index in the matrix. Then you know that this guy, because it's a k-independent set, will have elements in the main diagonal and zeros otherwise. Okay. If we denote mu as the smallest eigenvalue of this principal submatrix being corresponding to the k-independent set, by Cauchy interlacing, we can prove some things easily. We know that there are at least the order of the k-independent set eigenvalues of this P of A, which are larger than the smallest eigenvalue of B. And we also know by definition that if this mu is the smallest eigenvalue of this B, this is larger or equal than the smallest entry in this P of A. Okay. So using a bit of interlacing, I didn't write down all the inequalities, but it's kind of a nice exercise on this other definition. It follows one of the bounds, and the other one is proof analogously. Okay. Using the others, so there, you remember there were two M inequalities in interlacing, you can use the other M to prove the rest. Okay, and the second result we extended with Coutinho field was the Hofmann type bound, but in this case, it looks different than the previous Hofmann type bound. The one that Job was asking me used the expander mixing lemma extension. Here, we don't require any properties of expander graphs. Here, we are just going to apply the second type of interlacing, and then we obtain a bound for alpha k, an upper bound for alpha k for regular graphs. This is important to note, the regularity here. This assumption is a very natural assumption just because otherwise you get a zero here and well, some technical things, but nothing important. So for the previous bound, we did expander mixing lemma, but now we're going to do interlacing with quotient metrics. So let me give you an idea of the proof. It's a bit of same style. We start considering a k-independent set that we denote U of order, in this case, R or U. And then we consider, because the second type of interlacing required to have a partition of your vertex set or a partition of your adjacent symmetrics. So we consider a partition between the k-independent set and the rest of vertices. I didn't introduce what is a characteristic matrix, but you can imagine once you have a partition, a characteristic matrix just tells you which vertices are in each vertex set of the partition. So that's a bit the idea. You can calculate using this characteristic matrix how the quotient matrix look like. It's a bit technical, but is this size 2 times 2 because we only have two partitions, a partition into two sets. And then we also know that B has two eigenvalues, and we know that the trace should be the sum of eigenvalues. So we can already, with these two things, get some information on the eigenvalues. The other eigenvalue comes from constant row sum equals mu sub 1, the largest eigenvalue, because we are assuming regular graph also. Then by the second Hammers interlacing, by the second result by Hammers, the result follows. So this proof is much easier than the one we use expander mixing lemma, shorter, and to me it's a bit more neat, so you don't request so much somehow. So this bound improves the previous bound because it's more general. It's still for regular graphs, obviously. We require regularity as well. And it's sharp for some values of k, as I will show later computationally. And then, of course, for the case K1, if you take the polynomial that is just x, so you consider A instead of any power, then you obtain the, after getting the right values of the parameters in the bound, you obtain the well-known ratio bound by Hofmann. Okay? Then for some cases of these bounds, because again, this bound is super generic, for some cases you could think, okay, maybe for K2, maybe we can get a very good polynomial or best polynomial. So yes, you could do that with some calculations. For K2, for a regular graph, we were able to find the best polynomial that upper bounds this alpha 2. Of course, for K3, finding close expressions for this bound is hard, I would say. That's why later on we just provide an optimization method. So let me just give you some comparison results for K2. When I write down time, it was longer. So we just stopped the simulation. But so this is the bound we should look at because it's the improved bound. It's quite decent. And maybe it's important to notice that Lovász bound, because maybe many of you probably are thinking like, yeah, but Lovász bound is there, and Lovász bound can be just applied to the power graph, and that's correct. So we also compare our bound with Lovász bound, the SDP bound. So in many cases, it behaves quite nicely. Of course, it cannot beat Lovász bound. I will mention it why in a second, but yeah. It was quick and it behaves quite nicely. That was a bit the main findings we realized about the bound. So as I mentioned, Lovász theta function provides also an upper bound for the independence number, and therefore obviously also for the k-independence number, because it's just the independence number of the graph power, right? So we just apply Lovász bound to the power graph to compare with our bound. So, but we also know by this Lovász result in 79 that Hofmann's bound, the bound we are extending, it's also an upper bound for the var theta, the theta number, which means that our Hofmann type of bound will never be able to beat Lovász theta number of the power graph, right? However, we also notice that for small cases, I'm not claiming this in general, solving the MILPs was quick. And I will explain the MILPs in the coming slides, than solving the SDP bar for calculating the Lovász theta number. And in many cases, our bounds perform decently, quite good, actually. So now we are in the step that we could think, okay, is there further optimization possible? The answer is yes, by using mixed integer linear program techniques to implement the bounds. And sometimes, assuming extra properties on the graph, you can even push this optimization further. And this is joint work with Coutinho, Fiol, Nogueira, and Salamaker. So main two questions are, what is the best polynomial for a general K, for alpha K, for the bounds? Del Sarte provided in 73 an LP bound on alpha of the power graph for distant regular graphs. Lovász proved the SDP bound, as we just saw, which also gives an upper bound for the alpha K. And what about this Hofmann type and inertial type of bounds that we just proved? For the Hofmann type of bound, the optimization was done very recently by Fiol using linear program techniques and assuming walk regularity. I didn't mention it here, but this is also important. So you lose generality when you optimize the bound, basically. And for the inertial type of bound, this is exactly what we are going to do now. Okay, the optimization of this inertial type of bound. So we want to optimize this bound that you have here. You see, we want to calculate what is the best polynomial of degree at most K that minimizes this thing on the right-hand side. So we can assume, these are technical details, but we can assume the minimum of one side, as I did before in the proof, otherwise you just take minus the polynomial. And you can also translate, instead of double use here, you can also translate it to 0 and then add it to the polynomial later on, okay? Just to make our life easier when we model it. And then what we are going to be doing is like we are going to be using the spectrum where all the eigenvalues are distinct. And this is equivalent, this optimization problem is equivalent to minimizing the number of eigenvalues, lambda j's, sorry, this should be theta j's, like here, that are larger or equal than 0. So we are counting the number of eigenvalues that evaluated in a polynomial that we want to find. That polynomial gives larger or equal than 0. And we are adding up those eigenvalues. Mj are just the multiplicities of each eigenvalue. Okay? So we assume that there is a graph with this spectrum, as I mentioned. This is the polynomial we want to optimize. We need to use these two extra. B is a vector of variables, and M is a parameter vector. So this MILP that I'm going to show has this number of variables. D is the number of distinct eigenvalues of a graph, which for highly symmetric graphs, these numbers sometimes are very low. K is the alpha K, so whatever you're aiming to compute, and plus 2. And this is the optimization problem, the first method we provide. So let me go through it a bit. Maybe the important constraint here is the one that has an asterisk, because that's a constraint that is going to count when the condition that we want to count happens, when we want to minimize the number of polynomial evaluated in the number of eigenvalues that evaluated in that polynomial are larger or equal than 0. So this condition with asterisk gives that when this is the case, implies that Bj is 1. That's why in the objective function, we are actually counting how many times this happens. We want to minimize this number of eigenvalues that hold this condition. Okay. So actually, we do it for each vertex. That's a bit the handicap of this part. And then you find the best objective of all of the solutions you find. Okay. So for large graphs, you can already imagine this takes a lot of time. However, this bound is very generic. It doesn't require any regularity as the ratio type of bound or as Fiol's optimized bounds. The question now is like, can one avoid running this MILP for each vertex? And the answer is yes, if you assume the very first concept I defined of K partial walk regular, because recall that in this case, the entries in the main diagonal of the power linear combination of power matrices is just constant, right? So you can run it for one vertex and then you know it for the other ones. Okay. This is just a remark. Okay. So for this case, I'm not going to now go into details because it again uses the predistance polynomials, which I didn't define. But in this case, you can get rid of the first two set of constraints. So we only need to run these MLP ones. Okay? And then, for instance, we find some families of graph for which is bound is tight. By running this MLP, you can actually go through many families that pop up in your mind and then see if some of them give the best result. For example, for odd graphs, this bound, prism graphs, also thing, and some others. Now, here is when quantum appears, maybe finally with last minute. But why is this optimization interesting of this inertial type of bound? This is interesting because this inertial type of bound, the one that contains this generic polynomial of degree at most k, is also an upper bound for the quantum k-independence number. This is a result we proved recently with Elphik and Vokian. And this justifies also the use of MILP techniques to optimize such bounds, because you know all probably that it's not known if this quantum independence number and quantum chromatic number are computable functions. And there is also the sandwich theorem or results that give you that the bounds actually holds for the quantum counterpart. I'm going to skip this because I'm running a bit out of time. But this was an alternative bound inertial type of bounds, where instead of counting larger or equal than 0, so instead of looking at polynomials in eigenvalues that are larger or equal than 0 or smaller or equal than 0, we get rid of the zeros. So you have the hope that when the spectrum behaves nicely, the zeros are not counted, then the bound can be even pushed farther. So we propose a new MILP. I'm rushing a bit because I want maybe to focus more on the last part that you might be more interested. So we also model this second type of inertial type of bound. And this is a bit the summary of what we have seen so far. Okay, so let's go now to the quantum part. I must say maybe here I'm really not an expert in quantum, so I was a bit afraid to speak here, but correct me if something I say is wrong or whatever, or maybe if you have some idea. So the whole thing started in September 2019 when I attended a workshop in quantum, combinatorial and analytical aspects of quantum information theory. So I was very glad to be invited. I learned a lot from that workshop, but at least I got a bit familiar with the definitions of quantum graph parameters, which I was not familiar before. And at the same time, it was a good coincidence with the timing. There was this paper on arXiv, which provided an inertial upper bound on the quantum independence number of a graph. So of course, that caught my attention first because of the inertial bound, and second because I was in the quantum workshop. So I had to look at this paper by Vokian and Elphik. And what they prove is actually that for the quantum independence number, the inertial bound also holds. So you remember the classical inertial Svetkovic bound. That tells you that that's independence number, and in this case, the quantum independence number is upper bounded by the minimum between the number of positive eigenvalues and negative eigenvalues. They prove it for a weighted adjacency matrix. I just prove it for the adjacency matrix with the previous results. So main question, of course, is like, does it apply for the quantum independence, k-independence number? And the answer is yes. And it was not very hard, and they were really kind. They told me, you want to join the paper, and okay. That's how it went with the story. But now let me explain a bit more of consequences of this bound, maybe. So you probably know what the trace inner product is between two matrices. It's just a trace product. And then, of course, in the paper they use, in the paper by Vokian and Elphik for the quantum independence number, they use this definition by Laurent and Piovesan, or maybe it's a classical definition. I'm not sure to whom to refer it. But the main thing here is like it contains the identity condition, but then two orthogonal conditions. And the only thing one needs to check is like, okay, for the k-independence number, instead of requesting this orthogonal condition for each edge, which is in the independent set, now you need for each, well, I will mention it in a second, for each pair of vertices at distance at most k, this orthogonal condition will have to be 0. So you can already see or predict what's coming next. Maybe it's also important to recall that the quantum counterpart upper bounds a classical version of the independence number, and the classic case corresponds to the dimensional projectors of dimension 1. So for the k-independence number, one just needs to rewrite very slightly the definition, and yeah, the same thing will apply. So this is what we changed in the previous paper by Vokian and Elphik. And then a bit of motivation of this, in quantum information theory, you know it better than me. This difference between the quantum parameter and the classical parameter seems to be a good measure of the benefit of using quantum entanglement. We don't know if these quantum counterparts are computable, and then there are also a bunch of papers out there that give bounds and things for quantum independent and quantum chromatic numbers. So actually, the inertial bound for the quantum k-independence number is exactly the same as the most general bound I proved using the interlacing, okay, with a polynomial applied to the eigenvalues. And this is just a technicality. We had to use this projective packing number that Robertson defined in his thesis, but it's not relevant for us. It's just because it makes the proof easier, because instead of dealing with two types of orthogonality conditions, you only use one. And in particular, this result implies that the quantum independence number is upper bounded by this inertia bound, the classical inertia bound as well, okay? So other bounds for the quantum independence number, yes, there are several, at least two that I know. Maybe there are more that I'm missing, so please tell me if that's the case. It was proved by Lovász, I already mentioned that this Hofmann bound is upper bounded by the theta number by Lovász. So in particular, because of this sandwich thing, this Hofmann bound is also bound for the quantum independence number. And there is also a bound that uses Laplacian eigenvalues and does not require regularity in the graph. So maybe it's a less famous bound. This bound was also shown to be true for the theta number by these people here in 2019. So this second bound by Van Dam and Hammers is also an upper bound for the quantum independence number. Okay? So there are other bounds for alpha Q, but there was no inertia bound until recently, or it was not known if it was true, but it's true indeed. More consequences of this result. Of course, this is just a case of alpha, so quantum independence number without any K1. We prove at the very beginning, you remember, like the inertial type of bound for alpha K, for the classical parameter, was sharp for some infinite families of graphs. And since these inequalities hold, these families of graphs also provide sharp examples for the quantum counterpart. So for these families, it seems that there is no benefit, if I'm not confused with this benefit between the difference, from using quantum entanglement for independence at least. More conclusions. Okay, we also, you can also say that when the inertia bound holds with equality, it has to happen that because of the sandwich theorem that this quantum independence number equals the classical version. And this happens, we tested on SAGE also for some graphs. Like here, I just named some of them. And finally, just almost finished, like there was a question in 2010 that asked whether there exists a real symmetric matrix for which the inertia bound holds with equality, not for adjacency, but for any weighted matrix, symmetric. They proved computationally that this is true at least for graphs up to 10 vertices, so they thought maybe it's true in general. But actually, Sinkovic disproved this recently, proved that there is no such a matrix for which this inertia bound is tight, in general at least. However, this is still, I mean, it leaves the open question still to know that if there is still maybe always a weighted symmetric matrix for which this bound or this inertia bound holds with equality. But because of our result, every graph for which there is for which the classical independence number is strictly smaller than the quantum one, those graphs could just lead to new counterexamples for which this question is true. So you can disprove it for at least this condition when alpha is strictly smaller than alpha Q. Okay. So finally, let me end up with some open problems. Maybe one of the main questions, like, can we use the techniques, the MILP that we proposed in the last paper, to optimize this inertia type of bound that depends on the polynomial of degree k, to find more families of graphs for which the quantum k-independence number equals the classical k-independence number. Of course, for the case k1, this is nonsense, because then you just have the inertia bound and then it's what it is, you cannot optimize. But for bigger case, for larger case, this could be an interesting question maybe. Well, I think this is an open question, famous open question in quantum community, so maybe I will not spend too much time on it, but this is, I think, open, if I recall correctly from the workshop. Find the graph with the smallest number of vertices such that the classical independence number is strictly smaller than the quantum version. And there were some results already out there. At least the smallest case was this by Laurent and Piovesan. And maybe more open problems, now going back to the spectral part, to the classical spectral graph theories, like, can we use same type of methods, optimization methods, to find other best polynomials for some graph families or for other values of k, maybe, closed formulas? That could also be interesting. We did it for k2, but it could maybe be done for k3, I don't know. Maybe interesting also, the best polynomials for the ratio-type bounds in some cases resemble the best polynomials for some graph families for the Inertial-type bound. And this is a question I want to work in the future, like, can we find some clear relationship between both bounds, the inertia bound and Hofmann bound, the classic bounds, not even the extensions. This is not known to be the case, and I think it would be really nice. You saw the proofs go with interlacing both of them at different types. It would be nice to have a link between both bounds because both are quite relevant. Next, a natural question also, what is the complexity of such proposed, the MILPs we use to compute the best polynomial? And that was all from my side. Thank you very much. If you have any questions, please just ask me.